Welcome to Spring LIB.
Okay, so today we're going to talk about energy conservation. So energy conservation is a special case that happens when the only forces acting on a system, the system that we are studying, are conservative forces. Okay? And conservative forces are the ones that can be expressed in terms of a potential. An example of this is gravity. Okay? Okay, so conservation of energy is going to say that the energy of your system in an initial state, EI, is going to be equal to the energy of a final state, EF. Okay, this is the expression for energy conservation. Now, in this exercise, we're going to see an application of this principle in the following. So suppose we have a pendulum. So we have a pendulum of length on which we have a wire of length L that is known to be equal to 2 meters. And in the edge of the wire, we have a small ball. Okay? A small ball of mass equal to 70 grams. So 70 times 10 to the minus 3 kilograms. Okay? So this is a pendulum. Now, suppose that we know that we release our ball in the angle theta 0, release it from rest, such that theta 0 is 30 degrees. Okay? So given this, what is going to be the velocity of the ball when theta is equal to 0? So what is going to be the velocity of the ball in this point? Okay? Okay. So we want to find the velocity. So remember first that the velocity for rotations can be expressed in terms of the angular velocity. This is the linear velocity. And it's going to be the angular velocity that I'm going to call theta dot times the distance between the particle that is rotating and the center of rotation. So here, L. Okay? Now, in this case, what are the forces acting in our system? So the only force that is acting in our system, that is the small ball, is the gravitational force. And I told you that gravity is a conservative force. So since the only force is a conservative force, we can use conservation of energy. We have conservation of energy. Okay? Now, an expression we can use for conservation of energy is that the total energy of the system at this point, when the ball is released from rest, has to be equal to the total energy of the system when the ball is making a zero angle with the horizontal axis. Okay? So EI has to be equal to EF. Okay? So let's look at the initial state. So when the ball is making a 30-degree angle with with the vertical axis. Okay, so since there is no velocity, the kinetic energy, the initial kinetic energy is going to be equal to 0. And we're going to have only the gravitational energy that I'm going to call U. Okay, so what is going to be the gravitational energy in this case? First, to find the gravitational energy, we have to choose a place on our system to be the zero for gravitational energy, because since gravitational is a potential, the only thing that interests to us is the difference. Okay, so if we put this point making a zero angle to be our point of zero gravitational energy, then we're going to have that the gravitational energy in this point here is going to be mg times h, on which h is going to be the distance between the vertical projection. So let me put this in green, and the total length of the wire. So it's going to be this thing here. Okay? Okay. Now, we can see that h is L minus L, the projection into the vertical axis. So L times cosine of theta 0. Okay, so let me just put L in front of everything. L cosine of theta 0. Okay, so we have the initial energy of the system is going to be only mg times L times 1 minus cosine of 30 degrees, or theta 0. And this is going to be equal to the energy when the ball is making 0 degrees. Okay, when the ball is making 0 degrees, the potential energy is going to be 0, because we set this specific point to be our 0 gravitational potential point. And the only energy acting on the system will be the kinetic energy. Okay, and the kinetic energy for rotation, if you remember, is the moment of inertia times the angular velocity squared divided by 2. But the moment of inertia for a particle that is rotating around a point that has that is at a distance L between to the particle is going to be the mass of the particle times the distance between the particle and the center of rotation squared, theta squared. Okay, we can isolate the angular velocity. So first, you can notice that we can cancel out the mass of the ball, and we're going to have that the angular velocity squared is going to be 2gl 1 minus cosine of 30 degrees divided by L squared. Okay, we can cancel out L with L squared, and we can rewrite the angular velocity in terms of the linear velocity, which is the quantity that we want to find. So this is going to be V squared divided by L squared. Okay, now taking the square root, we're going to have that V is going to be, it's going to be L times the square root of this term. So 2g, which is 9.81, times 1 minus cosine of 30 degrees divided by the length of the wire, which is 2 meters. So doing this calculation, we're going to find that the velocity at the bottom for the ball in the pendulum is going to be 2.29 meters per second. Okay? Now, question B. We want to find again the velocity, but now not for the point that makes a zero angle with the vertical axis, but for the point that makes, a 15-degree angle with the horizontal. So we want to find at this point here that makes an angle theta that's equal to 15 degrees. Okay, we once again use conservation of energy. So the initial energy of the system we calculated in question A is mg it's mg 1 minus, it's mgl times 1 minus cosine of theta 0, on which I'm calling theta 0 30 degrees, okay? So this is the initial energy. Now the final energy is going to be the kinetic term, moment of inertia times theta dot squared divided by 2, plus the potential energy from gravity. Now, you can see that this time the height is not going to be 0 because we set 0 to be here. Okay, so this is our u equal to 0, making a 0 degree with the vertical axis. So h is going to be this height here, which is just 1 minus cosine of 15 degrees. Now we can equal these two expressions. Okay, we have that mgl 1 minus cosine of theta 0 has to be equal to ml squared theta dot squared divided by 2 plus there's an L here, mgl 1 minus cosine of theta. Then we can isolate the angular velocity. So theta dot squared. Notice that we can also cancel out the mass and cancel out this L here. Okay. We're going to have that theta dot squared is going to be equal to 2 over L times 1 minus cosine of theta 0 minus 1 plus cosine of theta. Okay, we can cancel out 1. Now, we can again rewrite the angular velocity in terms of the linear velocity and substitute the values that we already know. So v is going to be L times the square root, there is a g in here, square root of 2 times g divided by L. Sorry, I told you that I'm going to substitute the value. So 2 times 9.81 divided by 2 times cosine of 15 degrees minus cosine of 30 degrees. Okay? Doing this calculation, we're going to find that the velocity is going to be 1.98 meters per second. Okay, now question C. Want us once again find the velocity, but this time we want to find the velocity when the ball is making a 15-degree angle to the left, okay? Here. Previously we calculated to the right, now we want to calculate to the left. So theta. Okay, so you can notice that since the angle and in respect to the vertical axis is the same, no matter if you're looking to the left or to the right, then the answer is also going to be the same as the one that we calculated in question B, because theta here is 15 degrees. So no matter if it is left or right, if it's the same angle in respect to the vertical, the answer is going to be the same. So V here 1.98 meters per second again. Now question D. Question D wants us to find the tension on the wire for each point, for the points of question A, question B, and question C. Okay, so D, A, what is the tension when the ball is making a 0-degree angle with the horizontal? With the vertical axis. So let's draw it here again, our system. We have our ball like this. The only force acting is the gravity, and the gravitational force is pointing to the same direction as the tension. Since the ball is not moving upwards and nor downwards, that is, since the ball is not floating or sinking, is standing still like this, we're going to have that the net force in the y direction is equal to 0 and is equal to the tension minus the gravitational force. So the tension is equal to mg, on which m is 7t times 10 to the minus 3 kilograms, and this times the gravitational acceleration. So you're going to find that the tension for the point of question A is going to be equal to 0.686 newtons. Okay, pretty simple. Now we want to find the tension in the point that we calculated on question B. So the tension when now the ball is making a 15-degree angle. So the ball is like this. Okay? So we have the gravitational force pulling downwards. And you're going to have a tension pushing in the direction of the wire, okay? Now we can see that there is going to be a component of the gravitational force that is pointing in the direction of the tension. I'm going to call y, okay? And from Newton's second law, we're going to find that, okay, since the ball is not going in this direction, nor going like this, we're going to have that from the same argument we did in here, that the projection of the gravitational along the direction of the wire is going to be equal to the tension. Okay? And it's going to be mg times this angle here is theta, so cosine of 50 degrees. Now the tension is going to be equal to 0.594 newtons. And for the point in question C, so the tension when the wire is making a 15-degree angle to the left, okay? Since theta is the same angle, so you can see that gravity downwards, tension along the wire, and we're going to have the projection of the gravitational force here. The angle here is also theta, so it's going to be the same thing as we did for dB. So T is going to be also equal to 0.594 newtons. Okay. Now, our last question, question E. Question E asks us to recalculate the velocity, the linear velocity of the ball in the same points of questions A, B, and C, but now we must consider that the ball will have an initial velocity of 1.2 meters per second. Okay, so let's see how this will affect our calculations. Okay, so in question A, we had that from conservation of energy, we have that the final energy was I theta dot squared divided by 2, and this was equal to mgl 1 minus cosine of theta 0, which is 30 degrees. Now we're going to have to also add a kinetic term for the initial configuration. So I over 2 theta 0 dot squared, okay, the initial angular velocity. Okay, now let's try to isolate theta dot. So theta dot is going to be just, so theta dot squared is going to be 2 divided by L times G 1 minus cosine of theta plus V0. Sorry, let's write in terms of theta plus theta dot squared divided by 2. Okay, so this is what happens when we isolate theta, recalling that I is ml squared here, such that we can cancel out m and l. Okay. Okay. Oops, sorry, I was forgetting a term. Is theta 0 dot squared times L. Okay. Okay, now we can substitute the angular velocity for the linear velocities and take the square root of everything. We are going to have that V. The new velocity is going to be, I'm going to write just the expression. I'm not going to substitute the values. It's going to be L times the square root of 2 divided by L times G times 1 minus cosine of theta plus V0 squared divided by 2L square root of everything. So you can notice that the only difference between this expression and the expression from questions A and B is basically that we are adding this term in here. Okay? We are adding V0 squared divided by 2L inside our square root. Okay? Now, if we substitute everything for the values that we have, that is L for 2 meters, G for 9.81, theta 0 for 30 degrees, V0 for 1.2 meters per second, we are going to find that the velocity is equal to 2.58 meters per second. Okay, so notice that this is greater than the value from question A. So when we put an initial velocity in our ball, then the velocity that we are going to measure at the lowest point is going to be greater than if the ball was falling from the rest. Okay? Now, find the same thing for the point of question B, but with the initial velocity of 1.2. Okay, so we want to find for theta equal to 15 degrees. Okay, now you could see from what I did in question EA that I told you that the only thing that was going to change in our calculation is that inside the square root, we're going to add this term in here. So basically what we are going to do is we're going to just rewrite the expression that we found in question B, okay? This expression here, but adding a term of plus V0 squared divided by 2L. Okay, so let's do this. You can see that we are going to save lots of time by noticing this trick. So this case is going to be, so we found to be 2 divided by L times G times cosine of 15 degrees minus cosine of 30 degrees. Okay, and now we're going to add plus the extra term coming from the initial velocity, v0 squared divided by 2L. Okay, you can just substitute the values, and we're going to find that this velocity is going to be 3.31 meters per second, which again is greater than the value that we found for question B when the ball was falling from rest. Okay? Lastly, we're going to calculate our velocity, but when the ball is making a 15 degree to the left. Okay? Now, as I told you in the beginning in question C, is that no matter if the ball is to the left or to the right from the vertical axis, what matters is if the angle it makes with the vertical axis is the same. And this is what actually happens. So this angle here is the same as the angle of question B. So if the angle is the same, then the answer is also going to be the same. So here the same thing, 2.31 meters per second. And this is the